Hey guys, in this video I'm going to give a little bit more detail on using Newton's second law to solve the motion of objects. Specifically, I'm going to talk about something called Newton's second law pairs. So these are pairs of forces, meaning two forces, which exist because we solved Newton's second law and found out they have to exist. So they're forces which are a result of Newton's second law. I want to do this in a specific case. I want to do this for a box which is sitting stationary on the ground. Okay, so there's my stationary box. If I want to solve Newton's second law for this box, the first thing to do is to write down all the forces. Well, I said the box is massive, so it has a gravitational force, so let me get that on the diagram. Okay, so there's my gravitational force. The next step is to see if I know of any other forces which should exist on this box. Well, let's say I can't think of any, and I say, okay, I'm done. The next thing to do is to check to make sure that this box has the kind of motion that you expect based on your free body diagram. So I have one force pointed downwards. That means the net force is pointed downwards as well. That means the acceleration is pointed downwards. And is my box accelerating downwards? No, it's not. It's stationary. I said it's stationary at the beginning of this problem. This is a box sitting on the ground. So something I did was wrong. The force I forgot about was the normal force. So because the box is sitting on the surface could possibly act on the box with a normal force, normal meaning perpendicular to the surface. And in this case, that normal force must be there because the box is not accelerating downwards. The floor is holding the box up. So I just did that intuitively, but actually I used Newton's second law to do it. So let me write down Newton's second law in this case and look a little bit more carefully at how I used Newton's second law to do that. First, I want to put a coordinate system on this diagram. So I picked a coordinate system with x to the right, y positive upwards, and now I'd like to write Newton's second law in this coordinate system. I have no forces acting in the x direction, so let's just write Newton's second law in the y direction. The left side of Newton's second law is just the sum of the forces in the y direction. The right side is 0 because mass times acceleration in this case should be 0. I said the acceleration was 0. So if I try to do this, I start with, okay, I have an FG. It's pointed downwards, so I'm going to write negative FG, the negative sign being downwards, and the magnitude of the gravitational acceleration is just going to be simply m times g. But I can't have just that force, right? I can't have this equal to 0 because I know the gravitational force is not 0. It's m times g. So I need something else here in Newton's second law, some other force, which is going to make the sum of the forces be 0. What other force could I possibly have? The normal force is the only possible example in this case. I said there's nothing else in the universe besides the Earth, which is pulling on the box, and the surface. So the only other possible interaction we have is the normal force. So that's obviously what needs to go in here. I could take this one step further and actually solve for the normal force just by moving this guy over here. I'm also going to put in m times g for that fg, and I can find that the normal force is equal to m times g. So using Newton's second law, I was able to determine that the normal force exists and also how big the normal force is. Okay, so now I have to stop and say something which many students have trouble with, and that is the size of the normal force. I just found that in this case the normal force is the mass times the gravitational acceleration. It's equal to the weight. How did I know that? Did I know the normal force is always equal to the mass times the acceleration? No. I knew that the normal force can only be found by using Newton's second law. Newton's second law is the thing which told me how big the normal force was. So that means the normal force is not always mass times the gravitational acceleration. And I can very easily come up with a case where that's not true. Let's say that I have another force acting on this box. Let's say that I am also pushing downwards on this box. And I've called that force F. So this is me pushing downwards on the box. Still stationary, but now has an extra force on it. Okay, well if I go back to Newton's second law, right here, I'm going to rewrite this, including the additional force. I have negative Fg because I haven't changed anything about that. The normal force should still be pointed upwards, so I'm still going to put plus Fn. But the final force, I have pointed downwards, this F, so minus F. That's the left side of Newton's second law. The right side is still 0 because the acceleration is still 0. So now if we look at this equation, we have now 3 forces summing up to be 0. And if I said, oh, what is the normal force? I could still solve it, right? Take this, move it to the other side. Move this to the other side as well. And I find the normal force is not equal to the mass times the acceleration. The normal force is equal to whatever force I'm pushing on it plus the mass times the gravitational acceleration. Now that's because I was pushing on the box, so the surface had to push upwards on the box harder in order to make sure that Newton's second law was still satisfied. So the lesson to take away here is not only what the definition of this Newton's second law pairs is, but also we found the normal force from Newton's second law, and that's the only way you can find the normal force. You cannot assume the normal force is mass times the gravitational acceleration. The only way you can find the normal force is to solve Newton's second law. All right, great. Thank you guys for watching. This has been Newton's second law pairs from Motion with Forces, and I will see you guys next time.